So for the third part of this talk, the last part of this talk, I'll concentrate on electrokinetically driven microfluidics. So I'm a little biased towards electrically driven microfluidics because that's the field I'm most familiar with, and I worked in this. This is my graduate work was in this field. So that's sort of the reason why one of the reasons why I'm presenting this. But the second reason is that, since HP already does electrically actuated microfluidics, this is pretty much a natural thing for HP devices to do, or one of the natural things. The other things are also very much accessible as well. But today, in sort of the time we have, we'll talk about electrically actuated microfluidics. So what we'll talk about is that we'll talk about most basic things in electrically actuated microfluidics, and that is electrophoresis and electroosmosis. And those are actually very related phenomena. They're sort of an inverse of the other. And then I'll talk about the four most common and most basic techniques of electrically actuated microfluidics, and that is isoelectric focusing, isotechophoresis, dielectrophoresis, and electrowetting. And so here you sort of kind of see the examples of various little devices that use this. So what is electrophoresis? So electrophoresis is basically a balance of the drag that a particle experiences with an electrical field that the particle experiences. So if you remember Coulomb's law, that states that the force on a charge, or force between two charges, is proportional to the value of each of the charges, and inversely proportional to the radius squared of the two charges. And there's some sort of proportionality constant, usually Coulomb's constant, that determines this force. And based on this, you define an electric field by setting one of these charges as a test charge. So you say Q test, and then you say, well, the force in a particular electric field is proportional to that electric field and proportional to the actual value of that charge. So that's the electrical part of electrophoresis. And the fluidic part of electrophoresis is Stokes' law. So Stokes' law, this is actually a real law. It's empirical, completely empirical. It's an observation. Stokes' law actually is not an empirical law. It's a very valid equation, but it's actually derived straight from Newton's law, Newton's second law of motion, which is most of you recognize as F equals ma. F equals ma is a simplification of that law, actually. But from that, going through Navier-Stokes equations, which are derived from that Newton's second law of motion, and simplified to low Reynolds number flows, you obtain that a force on a spherical particle is proportional to the radius of the particle, okay, to the velocity that the particle is traveling at, and to the viscosity of the fluid. Okay, and this is valid for low Reynolds number flows. So usually, typically for Reynolds number less than 1, but you can still do this for Reynolds numbers quite low, even quite higher, even Reynolds numbers of 10. This is still fairly applicable, this equation. And interestingly, the other domain, so this is high, how big of an object you can capture with this. And the second boundary condition is how small of a particle can you capture with this. And it turns out that even large molecules you can capture with this Stokes law, and it works quite well. And there's also very interesting theorems, mathematical theorems, that are derived based off this, is that, for example, if you have some odd shape that's not a sphere, so how do you estimate the drag on that? Well, it turns out, like for example, if you have a chair, a small enough chair that this Stokes law applies, you can put a spherical shell around that chair, and you can put inside of the chair you can put a small spherical shell, and the drag, it's proven by this theorem that the drag is bounded by the two. Sorry. And so this is a fairly powerful law, even though it's very simple. And so if you combine this, so if you recall, you can use this for very small things, even like ions. If you combine this with this equation, you directly combine and balance the forces as you would on this body, you would find that the velocity, right, that comes from this equation is proportional to the electric field, it's proportional to the charge, and inversely proportional to the radius and the viscosity, right? And this proportionality, this entire proportionality thing, you call this an electrophoretic mobility. Now, this is a little bit simplified. Electrophoretic mobility scales like this, but it's not exactly this. And the reason for this is that this radius, for most objects, is not just, an ion is not a hard body like, this chair where you hit it and you know where its dimensions are. Ion has this probability cloud of electrons around this, for example. So this radius is a little bit tricky, but as a first approximation, this is what we will treat as electrophoretic mobility, and that is how it scales. Okay, and so there's also secondary effects, right? A charged particle, for example, would attract other charged particles in the water, for example. Say this is like a sodium ion. In the water, there are some chloride ions that you dissolve in the water as well, and they'll be attracted to this. And as you apply a field to drag this positive sodium ion in one direction, while the chloride ions, of course, are going to go in the other direction, right? So if they do this, and they surround this particle, they impart some drag on this particle as well, and so that sort of lowers effectively electrophoretic mobility. This is sort of this cloud. And this effect is also depends on the concentration of the solution. If you imagine if the concentration of the solution is very concentrated, there's a lot of chloride ions, they kind of bunch up next to this. And if the solution is more dilute, then they kind of are farther away from this positive ion. They're kind of free floating because there's less of them pushed, they can float farther away. And so the drag on this is a little bit less, and so the electrophoretic mobility is higher. So you'd find that the mobility of ions changes with the concentration, and typically it's higher when the solution is more dilute. So this is kind of a secondary effect, but it's an important effect for this. And it turns out that the solution conductivity, right, is ionic conductivity scales with how much current you can carry, right, for a given voltage, and that is related by how much current is. Ions are ones that are the charge carriers. They're the things that carry the current for you, and so if they're faster, you get higher conductivity because you can carry more current for a given voltage, or you can use less voltage to push the same amount of current. You can think of it that way. And so the conductivity is, of course, the sum of the concentration, so how many you have per given volume, and how fast they can go, right, their mobility. And so if you scale the conductivity by the concentration, you find that that ratio is actually higher when the solution is more dilute because your mobilities are higher. So you'd find, and that's often a measure of this mobility directly, you measure it with the conductivity of the solution because that's fairly easy to measure. Okay? So that's sort of the basic of electrophoresis. And so real practice of electrophoresis, you don't usually, the most common electrophoresis is to figure out the DNA mobility. Okay? That's one of the most common applications of electrophoresis. And so, turns out, if you have DNA, right, it's a long chain of monomers, and this base pair is basically a base pair corresponds to a pair of monomers if it's double-stranded. And here is plotted is this electrophoretic mobility of this. And you notice that for small numbers of base pairs like 10, okay, to maybe 100, there's a significant change in mobility as a function of you adding more bases, okay? Versus if after that, after 100, your mobility, for some reason, is constant, is more or less constant, right? And so why do you think that is? If anyone can venture a guess why that is.
Conformation.
Okay. Conformation of the chain, okay. That's actually the right answer, or one of the right answers. Anybody else? Other answers? Or like more? What if you can you elaborate? What about the conformation?
A short chain will swing around and fly all over the place. As it gets to be long enough, it'll start coil and bundle into some shape.
Yeah, that's exactly right. So short chains they're fairly linear. They're more or less linear. And as the chains become longer, they kind of start, they try to coil more, and then eventually they become so long that they coil into a ball. So then you go from something that's spaghetti-like to basically something that's like a ball of yarn. It's not as tightly coiled, of course, as a ball of yarn, but it's this kind of ball, and what winds up happening is that here you have this ball of charge, and it has a certain radius, and you cannot distinguish it. Okay, so what do, right? You want to separate DNA in these lengths, so what do? Okay, so what you do is you take this polymer, which is your DNA, and you put it through another polymer, which is this gel, sort of matrix of polymers, right? So as it's traveling through this gel, it is often forced to sort of uncoil itself, at least partially uncoil itself, as it weaves through these like fibers of that gel, okay? And as it does so, it interacts with the gel, and so those interactions are very simple. They change its mobility, and you can tell, you can now separate, this is from 100 to 10,000 lengths, monomer lengths of DNA, and you can see you have significant changes in mobility, and you can also tune that mobility by tuning the concentration of your gel. So by tuning the kind of how dense this kind of forest that the DNA is trying to find itself through, you can tune this property. Okay? And there's also another advantage to gels is that once you have the gel, it just sits there. The gel kind of limits the diffusion of the DNA. So as it's traveling, it's not as diffusing as much inside the gel. Okay. So how do you actually do this in practice? Well, what you do is you take basically a slab of gel, just like you would make Jell-O. You take agarose instead of collagen that you buy, or flavored gelatin, because you buy gelatin. Flavored gelatin, you pour it in your Jell-O cup and put it in the freezer. Just the same, you just buy agarose, which is very similar. And you put it, and you pour this slab. That's the simplest way. You add also when you're pouring this buffer to keep the pH in that gel at the pH that you actually want. You pour this, you poke these holes into this, so they're just nice. There's really no reason to make for them to be like rectangular like this. It just makes them nicer. And then when you run it, you get these nice little bands. And so when you apply electric fields to this box with buffer and some DNA with some dye in this, you apply this and you get this sort of separation. And the separation is by the size that you have. So for example, here you have numerous amounts of sizes that you run, and different layers will have different sizes. So if you take a DNA and you cut it with certain enzymes that cut at certain locations, they're called restriction enzymes, and oftentimes they're specific to the particular sequence of monomers. You cut it up, the same DNA the DNA that used to be about roughly the same length, but different sequences, these enzymes would cut it at different locations, so the result would be different lengths of DNA, right? And if you do this, the fragments would be of different lengths, depending on their sequence, and then you can sort of tell the two apart. You can tell one is different from the other based on the sizes of the pieces that you got from these enzymes that could cut at particular monomer sequences, okay, base pair sequences. Okay, so it's a very common thing that is done in forensics to tell one person from another, like for example, the perpetrator of a crime from like bystanders at the scene or the victim, is by using restriction enzymes to cut up the DNA that you found and you amplified. So what I showed you with this piece of gel in a box that you cast and pour, that's fairly labor intensive. That's sort of the old school way of doing it. And if you go to universities and labs, you still find people do this kind of gels. It's labor intensive, but it's tradition, so people do it. If you want to do this sort of faster and you don't want to cast a gel and you want it to be more reproducible, you buy gels that are already prepackaged into these nice little chips. And they're, gels are very uniform. It's very tightly regulated manufacture. It's not like you had a bad day, so you forgot to add the buffer. Something like this. Everything is good, and the instrument does everything for you. It both runs this, so applies electric field in a very automated way. You just press a button, and it does it. And also, instead of you looking at the gel, where are the lines? As the lines go by the detector just records it in memory, and you get this kind of picture. So, for example, this is the time, and first, some sort of marker went by. Then we're going forward in time. Then this piece of DNA went by the detector. Then this piece of DNA went by the detector. So you get this sort of intensity as a function of time. And if you know by doing standard markers, you can tell the lengths of the DNA that are actually out there. So this is the adjuvant device. This is called an adjuvant bioanalyzer. It's an automated electrophoresis instrument that uses these microfluidic chips. Okay? And if of course, if your DNA is degraded, so it's all chopped up in many different sizes, you'd expect that it comes in and there's all sorts of sizes that you see there that's being chopped up. So very, very simple electrophoresis. Okay. So next is the complement of electrophoresis, which is electroosmosis. So electroosmosis, or maybe you have heard of electroosmotic flow. So in electrophoresis, you apply a field on a particle, a charged particle, and the particle moves relative to the fluid. Okay. So what happens if you take that same particle and you chain it to something, right? The particle cannot move, but it's still charged, but the particle cannot move. Well, because of Newton's third law, is that every action there's a reaction, then the fluid has to move. If the particle cannot move, the fluid has to move, right? And so in electroosmosis, this is exactly what happens, except now instead of a particle, the thing that is charged is the wall of the channel. So it turns out any surface, any surface, literally any surface, like this table, I could pour anything on it, like this liquid, be quite sticky. But if you put water on the surface, because the water and the table have different chemical potentials, they will have different electrochemical potentials, and so you would have a charge separation between the two. So if this table happened to be glass, if I poured water on it, glass will tend to take a negative charge because of the SiOH groups on the surface of the glass, and any positive ions that are in the water. For example, if it's DI water, they tell you there's no ions, right? Because deionized, it's not really true. Water breaks down into hydrogen and OH minus, right? Protons and OH minus, and so there'll be at least that in the water. At least if there's exposed to atmosphere, there'll be something else. There'll be carbonic acid, for example, but that's details. So there's always ions even these dielectric oils, there are some ions you can find. And those ions will go to the surface because now there's a negative charge, there's charge separation. And this causes an electric field in this direction, this is what brings these ions to it. And so if you take that surface, now you have your puddle on a piece of glass, and you apply electric field in this direction, this is free charge, and it will experience electrophoresis forces, right? So it will try to move this way, right? It'll try to move this way if you apply electric field in this direction. And as it does, these charges will hit water molecules, neutral molecules. They will hit the neutral molecules, and it will cause these molecules to go downstream as well, sort of follow them. And it will keep going, and it will start dragging the water behind them. And because these charges are at the wall, they typically start dragging the water at the wall, and the rest of the water is basically as if both walls are moving. It looks to the bulk of the water, it looks like the walls are moving. So the rest of the bulk of the water moves these charges along. And typically, these double layers are incredibly, incredibly thin. Basically, the analogy that is there to kind of make you intuitive is if this entire room was a microfluidic channel, like 10 microns, 100 microns, something like that on that size. That paint on that wall will be the thickness of this layer. Okay, that's sort of the relative scale. It's incredibly thin. So the bulk, like you guys, would not even feel. You feel like the walls are moving, and so you could just drive across. So this profile that's drawn here, this is the velocity profile of the water that will be moving, is actually quite exaggerated. It's almost going to be like completely like a top hat distribution. Okay, and that is a very interesting distribution all in itself, and leads to interesting phenomena in that if you have, typically when you have pressure-driven flow, the walls are not moving, of course, and the fluid next to the walls are not moving. So here is zero velocity, here is high velocity in the center, and so you have this kind of parabolic profile. And so things that are in the channel experience typically a parabolic velocity profile. So remember, if you remember a few slides back, where there was pinch flow fractionation, where the bigger particles, if you have a big particle here, it'll experience this high velocity profile and get separated out. We pull forward while the small particles here experience lower velocities that are kind of held back. You'll separate things out in the flow. Here, with this very sharp profile, that doesn't happen. And so it's actually helpful because things aren't sheared as much, and things, if you imagine things are sheared, right, if some things are going faster here and slower here, if you draw a line in the fluid, things are going faster here, they're slower here, they'll diffuse here. These guys from the center will diffuse here. You have an increased diffusion if you have a parabolic profile. If you have this nice rectangular profile, you do not have this. Things are sharper and